This is Module 4, the last video. We're going to go through parts E, F, G, and H for example 2. So it asks us here in part E, says based on the conclusions we made about persons A, B, and C above, which person's sample has the strongest evidence that people pick scissors less than a third of the time? So the question's asking us which person has the strongest evidence in support of the alternative hypothesis. Please note, we understand that stronger evidence means smaller p-value. Another way that we've now learned to understand strength of evidence is by way of the z-score or the t-score, the standardized statistic. We know that there is stronger evidence if your standardized statistic is bigger in absolute value. And one final way you can think about this is that we have stronger evidence in support of the alternative hypothesis if your sample statistic is further out in the tail. And so all we have to do to answer this question is go back and look at the p-values for persons A, B, and C. Look at the standardized statistics for these people and try to understand who has the smallest p-value, who has the biggest z-score in absolute value. So person A has a p-value of 0.34. That's a very big p-value. Person B had a p-value of 0.04, and person C had a p-value of 0.098. Similarly, for person A, B, and C, we could consider their standardized statistic, their z-score. Person A had a z-score of negative 0.6. Person B had a z-score of negative 1.7, and person C had a z-score of negative 1.4. So now we can see that person B has the smallest p-value. Person B also has the biggest z-score in absolute value. So that means person B has the strongest evidence in support of the alternative hypothesis. So person B has the strongest evidence of picking scissors less than a third of the time in the long run. Part F says person A and person B had the same statistical value. They both had a p-hat of equal to 0.3, but person B had a smaller p-value. It has to explain why they have a different p-value even though they have the same value of the observed statistic, p-hat equals 0.3. The reason for that person A and person B have the same p-hat but a different p-value, lies in the fact that their null distribution would have a very different standard deviation. Below I've copied a simulated null distribution for person A and for person B. The most obvious thing that you'll note, of course, is that person A had a much smaller sample size. The sample size for person A was 60 of rock, paper, scissors, and the sample size for person B was 600 games. When we look at proportion of successes for the null distribution, both are centered at the value of pi equals 0.33333. However, what you'll notice is that when you have a bigger sample size, the standard deviation of the null distribution is much smaller. Notice 0.38 is really at the upper end in the tail, unusual for the sample size of 600. And 0.28, again, is in the tail, an unusual sort of value to get. Notice where 0.38 and 0.28 fall in the distribution for person A. Here's 0.38, and here's 0.28. Those statistics in the person A null distribution are normal, usual, and expected, whereas in the person B null distribution, those values for the statistics are unusual. They're out in the tails. This, again, person B has a smaller standard deviation in the null distribution, and person A has a bigger standard deviation. We expect to see It is normal, usual, and expected to see a wider range of statistics for person A with a small sample size. It's normal, usual, and expected to see a small range of statistics for person B with a big sample size. So what I wrote is that since person A has a smaller sample size, the null distribution for person A would have a bigger standard deviation. Basically, the person A would have a null distribution that's more spread out. Since person B has a bigger sample size, the null distribution for person B would have a smaller standard deviation. So person B would have a null distribution that's more narrow. It would be narrower than person A's. That explains then why, even though they had the same sample statistic, that they would have much different p-values. Remember, they both had a sample statistic equal to p hat equals 0.3. So for person B, p hat equals 0.3 is here, kind of near the tail. The p-value would be calculated by finding sample statistics that look like that p hat and smaller. Whereas person A's p hat of 0.3 is very, very close to the center. And when you calculate the p-value for person A, there would be many, many, many more sample statistics like that and smaller. So I wrote that when they have the same value of the sample statistic, those sample statistics are located in a very different location relative to the mean. Person A's sample statistic is very close to the mean, whereas person B's sample statistic is quite a ways away from the mean. Person A and person C both had the same sample size of 60, but person C had a smaller p-value. Explain why they have different p-values even though they have the same sample size. Person A is on the left here. That's the null distribution for person A. And they both have and it has a sample size of 60, centered at 0.333, has a p-value of 0.343. Person C's null distribution is here, has a sample size of 60, it's centered at 0.33333, and it has a p-value of 0.098. Of course, these two are different. This is usually pretty easy for students to understand that these two are different because they have different sample statistics. Person A had a sample statistic of 18 out of 60, which is located here on the null distribution. And person C had a sample statistic of 15 out of 60, which is located further out in the tail. So since person C's sample statistic is further out in the tail, that means person C would have a smaller p-value. And part H. In part H, it says, we used a one-sided test for each of these hypothesis tests. Remember, we did that because our alternative hypothesis was that pi is less than 1/3. So when we calculated a p-value, we counted sample statistics that were like ours or less. That's one-sided. What would it mean to switch to a two-sided test? Well, first of all, it means to switch to a two-sided test that you would be using a not equal to symbol instead of a less than symbol. And that would mean, of course, that when we calculated the p-value, we would be counting sample statistics in the null distribution that were on both sides. We'd count sample statistics like our observed statistic and less. Then we would go to the opposite side of the distribution and count sample statistics like that and higher. So this would double the p-value, since you would be counting the same sample statistics that we did when we used a less than, and then we would add in the additional sample statistics on the opposite side of the null distribution. Since the p-value would be higher if we had to have double the sample statistics counted, that would mean we had less evidence against the null hypothesis. We'd have weaker evidence in support of the alternative hypothesis. In general, this is always true. If you switch from a one-sided test to a two-sided test, you've basically doubled your p-value, and therefore you have weaker evidence in support of your alternative. In general, on the very first page, these ideas have been summarized here. The further a statistic is in the tail, the stronger your evidence in support of the alternative. Second, holding everything else constant, a two-tailed test would be a weaker evidence in support of the alternative. And holding all other things constant, a bigger sample size provides stronger evidence in support of the alternative.